faculty addition to the Department of Physics. Rodrigo got his undergraduate degree at the Universidad de las Americas in Puebla, Mexico, and then went on to get his PhD at the Universidad de Granada in España, and then had postdocs at Lawrence Livermore National Lab and at Ohio University, and then joined us 2 or 3 years ago. It feels like you've been here for a long time, but it's really just been, I think it's just because so many things have happened since then. So anyway, with that, we'll let Rodrigo take us to talk about improving mass predictions.
All right. Yes, so this is my 3rd year actually here. Also, let me apologize in advance if you hear some noise. A neighbor has been using some kind of power tool this afternoon. It seems to have stopped, but it might happen again. And you might also hear a cat that is not even mine, but some neighborhood cat just really has taken some affection to us during this time. And now he cries outside of our door every time he hears us talking. So also apologize in advance for that. So yeah, I'm going to be talking about sort of some of the work that I've been doing in how do we improve mass predictions throughout the nuclear chart. And of course, the fact that we need to improve these mass predictions means that there is some uncertainty or some errors in our calculations of masses of different nuclei. And why is this important? Why is it important to know this uncertainty quantification, to know what is the error in our models? Well, first of all, uncertainty quantifications is sort of one of the main driving forces behind this theory experiment feedback loop. Like our experimentalist colleagues, they go and they make measurements. They know that there is an uncertainty in their measurements that allows us to then make our models and basically see whether or not our predictions fall between that error bar of that experiment. Then that means that there's also some uncertainty in our predictions, and then our experimentalist colleagues, they'll go and make new measurements, and then we'll sort of continue this process, improving both the experiment and the theory at the same time. They're also important because in nuclear applications, so I'm going to talk about this in just a bit, but nuclear calculations are one of the main ingredients in the description of astrophysical phenomena. So if there's some uncertainty in the input that we're giving to these astrophysical simulations, then that also means that there's going to be some uncertainty in those simulations. Also, it's crucial in the safety nuclear reactors. Like you want to know what are the sort of the limits of the parameters that you can run this nuclear reactor without sort of running into any kind of major trouble. And finally, they allow us to sort of estimate the error in our models. So even if I only have 2 models making predictions, well, if one of them is here and the other one is below here, are they really agreeing or not? Well, I don't really know unless they both give me the exact same number. But if they both have error bars, then there's a way for me to know they don't agree, or their error bars are overlapping, and therefore they do agree. They also allows us to extrapolate beyond the experiment. That is, if I want to make new predictions in areas where measurements have not been made yet, again, if I don't have an error bar of those predictions, then it's really hard for anyone to know whether those predictions make sense or not. And also, sort of, anytime there is a paper in Physical Review A, a theoretical paper, which is for atomic physics, now they also require to have some uncertainty quantification in that theoretical work. So even if it's just for the selfish reason that you want to publish, then that's also another reason why you should care about uncertainty quantification. That's still not the case for Physical Review C, which is for nuclear physics, but there are also journals who are only dedicated today to uncertainty quantification in nuclear theory in general. Another aspect that I was talking about, how these astrophysical simulations are important. So a couple of years ago, there was this multi-messenger observation of a neutron star merger, this GW, because they use gravitational waves to detect it, but they also use all kinds of different observational methods to observe these 2 neutron stars sort of going around each other until they collapse into a single place. And that resulted in sort of this big collaboration of more than 3,000 researchers from almost 1,000 institutions working together in one single paper. So that was a very long list of authors. Now, this one paper actually was just sort of the introduction, and then there were like several other papers where different groups worked on different aspects of this multi-messenger observation. One of the important aspects that came out of this event was that they confirmed that a neutron star merger, like the one here, is actually one of the sites of the R process. So the R process is this astrophysical series of chain reactions, nuclear reactions, that is responsible for the creation of half of the heavy elements in the periodic table. And these simulations, as I was saying earlier, they require several inputs, like, for example, the masses of neutron-rich nuclei, beta decay rates, also assumptions about what is the astrophysical environment. So now we know that a neutron star merger is that astrophysical environment, but there are other assumptions about the neutron star merger, and also uncertainties from both the astrophysical and the nuclear models, so that these predictions of how much of the different heavy nuclei is produced in an event like this one, then we should be able to put an error bar on that. Now, one of the problems with this is that of all of these inputs is that the R process is happening here on this area of the nuclear chart. So here I have number of neutrons on the horizontal axis, number of protons on the vertical axis. And we see that, for example, for other nuclear synthesis processes, like, for example, stellar burning, so where a star is just going through their usual life cycle and creating all these, it starts creating these light elements by combining neutrons and protons, and then it sort of goes all the way here, it runs out of fuel, and then it just dies off. So that's happening here in this region where we have a lot of information. We know these are mostly stable nuclei, we know their masses, we know their half-life. The R process, which is sort of responsible for the creation of all these other heavy elements, or half of them, is happening here, where we don't know anything. We haven't been able to measure anything about this nuclei yet. So what happens is that if we compare the abundance of these different elements, stable elements, the black ones on the solar system, well, for the light ones, the model and the observation match pretty well. But once we get to the heavy ones, sort of this agreement just goes away. And that is because even with our best simulations for the R process, our inputs are not the best that we can have yet. And that's why it's also important to improve our predictions here and to also know what is the uncertainty so that we can also put an error bar in these figures. So the fact that we have to come up with theory to say what is here, that means that we're going to have to solve the nuclear many-body problem. And there's two ways that we can go about it. One is called the ab initio method, or the first principles method. And in this method, if I have a nucleus here with neutrons and protons, well, the nucleus being a quantum mechanical system, I have to solve Schrodinger equations. So I have my kinetic energy operator, my potential energy operator, or my interaction here. If I do an ab initio approach, then for each nucleon, let's say for this proton here, I need to consider the interaction with every other nucleon that is there. So all of these green arrows. Then I would have to do the same for this proton here. So I would have to consider all the arrows that goes from this proton to all the other nucleons to construct my interaction. And then I should be able to sort of solve Schrodinger equation, get a wave function, get all the ground state, all the bound state energies. And this is what we call sort of a realistic approach, in the sense that if I know the interaction between each pair and I can sort of put them all together, I should be able to know what's happening here. Another approach is, instead of considering all these pairs, is to do what we call the mean field approach. We say, instead of looking at all these pairs, I'm going to say, well, for this neutron here, the interaction that is going to feel is just going to be an average of all the other nucleons that are there. And then if I want to look at this proton, well, the interaction that this proton is going to feel is also going to be an average of all of those. Now this is how I will create my potential energy operator, and then I can, again, solve my Schrodinger equation. But then this will be a phenomenological approach, because the mean field, the form of this potential that I'm going to create here is going to be one that I pick, that is going to make these calculations simpler for me, instead of having to go with this realistic interaction. And, you know, whatever it is, I'm just going to have to solve it. Whereas here, I'm going to pick one that's going to make calculations easier for me. So what happens with each approach? Well, in the ab initio approach, if the interaction that I'm using is sort of what we call chiral effective field theory, which is the most realistic interpretation of the interaction between neutrons and protons that we have is what chiral effective field theory says is, well, both protons and neutrons, they're made out of quarks up and down, and they're going to be interacting by exchanging gluons. Well, if I look at those as the degrees of freedoms, and then I just go back to the scale that I'm actually interested in, which is just neutrons and protons, well, at a first order, there's gonna be some contact interaction, but there may also be exchanging a pion. At second leading order, they're gonna be exchanging 2 pions in different places. I may also have a 3-body force. So this is like a very systematic way. There's a very systematic way to obtain all of these diagrams and to obtain what is gonna be the interaction between neutrons and protons. If we combine this interaction with an ab initio method, actually, a lot of light and medium nuclei are calculated pretty well. So in this graph, every blue box is a nucleus that has been calculated using an ab initio method and a chiral effective field theory interaction. And we see that for nuclei from helium-4 all the way to nickel-56, actually their theoretical calculation using this specific form of the interaction actually matches relatively well with the experimental value, which is this black line over here. Now, the problem is that heavy nuclei became out of reach because it's a problem of scaling, right? The more nuclei that I have, the more of these pairs I need to consider, and then the bigger my problem is, and then the more computational resources I'm going to need, and the longer I'm going to have to wait, or maybe it's going to be a problem that is so big that I will just be waiting forever. So the other approach is the mean field approach. And one particular implementation of that mean field approach is called density functional theory, or DFT. And what DFT does is says, well, the interaction is not going to be all those pairs. It's just going to be a functional of the density of neutrons and protons. So where they're close to the center of the nucleon, or where the nucleons are very close to each other, the density is higher, and therefore the interaction is going to be high. Where the neutrons and protons are farther away from each other, the density is lower, and therefore the interaction between them is going to be lower. Now, this, of course, sets a non-linear eigenvalue problem, because in order to know the interaction, first I need to know the density, and to know the density, I need to know the wave functions. And if I want to know the wave functions, I need to know the interaction, right? So the way that we solve it is, well, I just propose some density with some very simple form. This density allows me to create an interaction. Then I can solve that Schrodinger equation. Now it's just an eigenvalue problem. I have a matrix, and then I can diagonalize, get the eigenvalues, the eigenvectors. That is going to give me the wave functions. And now I'm going to be able to use these wave functions to calculate a new density. It's going to be slightly different from the one I had before. I'm going to calculate the interaction again. I'm going to get new wave functions, and I'm going to keep repeating this process until sort of the solution that I get for these wave functions isn't changing. So I get the same wave functions, the same density, the same interaction. Now, the good thing is that now this approach actually scales pretty well computationally, whether I'm solving helium-4, calcium-40, lead-208, oganescium. It doesn't matter how many neutrons and protons I have, because it's a function of the density and not of the actual number of neutrons and protons that I have. So the computational effort is going to be more or less the same, regardless of the system that I'm looking at. The problem is that I came up with this interaction on my own, just by one shape that made those calculations simpler. I will have to sort of fit some parameters to some masses and some other nuclear properties, but then there's no systematic improvement. Once I have that interaction, well, I may try to add more terms to the interaction, but I don't have this sort of nice order by order improvement that quantum effective field theory is giving me to work with this, with chiral effective field theory, sorry. So nevertheless, what is the state of the art of density functional theory? Well, right now it's sort of represented by the UniDef family of functionals. So these are different functionals here that depend on the density, and they all have between 12 and 14 parameters, and they're adjusted. These parameters, we adjust them to reproduce some nuclear properties, some masses and some fission properties. So UniDef 0 was that first. There's other families of, there's many other interactions, but I'm focusing on this one because those are like the most recent one and the ones that give a best global performance throughout the nuclear, or at least in the region where we have experimental data. UniDef 0 was the first one, and it focused only on spherical and deformed nuclei. Then unit of 1, they also added some nuclei with large deformations that actually improve the description of fission barriers. That is, how much do I have to deform a nuclei? How much energy do I need to deform it until eventually this nuclei sort of breaks down into 2 pieces? And then after that, it came unit F2, which added 2 additional parameters. It also added more experimental data. And sort of at the time, it was like, well, is this the limit of the mean field? Because what we see when we look at the difference between theory from unit F2 and experimental values in this region is we see this sort of clear pattern that actually matches the magic numbers of sort of when I have closed shells in the number of neutrons and protons. So here at 20, 50, 82, 120. And sort of because it's completely phenomenological and I don't have this systematic improvement, sort of like, is this how far we can go? Well, the approach that we proposed was like, well, let's try to combine both approaches and see if we can have sort of the best of both worlds. We're still going to have this mean field component where I'm still going to have these contact terms here, these 12 to 14 parameters that is going to account for the short range physics. I'm still going to need to adjust those parameters to reproduce some nuclear properties, some masses, some binding energies, some radii, some fission properties. And this is going to encode these many-body correlations the same way that all the other functionals have done before. But on top of that, I'm going to add this microscopic component that comes from chiral effective field theory, from this interaction between neutrons and protons that considers quarks and gluons as their degrees of freedom. Now, this component is going to only include the long-range physics, so it's mostly the exchange of pions. One nice thing is that this chiral EFT interaction is adjusted to NN scattering data and maybe some few 3-body data for the 3 nucleon forces. And it's going to be fixed at the DFT level. That means that whether I am adjusting my parameters or whether I'm making predictions once I've adjusted these parameters, this component is always going to be the same. And it's going to be the same whether I'm doing calcium 40 or whether I'm doing lead 208. Now that I have this microscopic component, I should have access to this nice order by order systematic improvement in the description of all of these nuclei. The one little price that we're going to have to pay is that we're going to have some non-local density that we're going to have to deal with. Right? Instead of this density that I had here that only depends on the relative distance, now it's also going to depend on the center of mass, or basically the 2 position of 2 different nucleons. Now, except for this little problem that we have to deal with, what I should be getting is sort of this scalable framework with systematic improvements, right? I should have something that allows me to calculate nuclei throughout the nuclear chart, but should also have these order by order improvements from chiral EFT. Now, how do we deal with this local density? Well, it looks like there's a lot of, so there's some kind of ugly integrals that we have to deal with. Now, my density depends on 2 variables, so the center of mass and the relative distance. And what we're going to do, like earlier when I had sort of only contact terms, that I had some delta functions here that allow me to take this integral and get rid of these non-localities. Now that I have some more realistic interaction that comes from DFT, I don't longer have those cancellations, sorry, from EFT. So what we do is something called the density matrix expansion. And the density matrix expansion basically says, take this non-local density and expand it in local densities and derivatives of the local density. So this rho of R, this delta rho of R, this tau of R is also a derivative of the non-local density. So it's kind of like a Taylor expansion for the non-local density. It's not exactly a Taylor expansion, but it sort of works the same way of, well, expand this non-locality around the point where you are local, where little r is equal to 0. And then this approach, there's some functions, some specific functions that you're going to have to make this expansion. But then once you do that, then you no longer have to deal with this non-local density. OK, so now that I have this new component, I need to readjust my 14 parameters. And what we're going to do is we're going to take unit F2 just as it is. We're going to add this microscopic component. And we're going to use the same optimization protocol so that we can make sort of similar comparisons between the unit F functionals and this new family of functionals. So I'm still going to have about 130 data, so some masses from the formed nuclear, the spherical nuclear, some pairing gaps, some fission properties. And here I'm looking at these least squares functions that we minimize when we try to optimize these functionals. And we see that already when I go from UniDev2 to when I add this microscopic component just a leading order, I already see a small improvement. When I go to next leading order, I see an even better improvement. And then it sort of seems that it plateaus. And then someone might ask, well, wasn't the whole point of this that you were going to have this nice order by order improvement? It seems like once you get to next leading order, you're not seeing anything new. And that's true for this least squares function that only has this 130 data. If I look at all the masses, so not only these ones over here, but I look at all the experimental masses that I know, well, and I calculate the RMS deviation, well, I see that UniDev2 and leading order, they're more or less similar. When I go to next leading order, including this delta excitation, I get a better performance. And when I go to next leading order, also with this delta excitation, it also gets better. I still have this sort of same structure that I had from UniDev2. It's just that the difference is now smaller and allows me to get a lot smaller RMS deviation. But I still have the same structure of this sort of peak, or those sort of dips going in the magic nuclide number. Other properties that we can calculate just to make sure that we're not making any funny predictions in other places. So we can look at nuclear matter and neutron matter. So that is when I have an infinite number of neutrons and protons, or when I have an infinite number of neutrons. So here I have all my different functionals without deltas, with deltas, with three-body forces, without three-body forces. And the comparison is here with these sort of pink pentagons that I have here. So these are some calculations from an Italian group in Pisa that they did their own calculation using a Carroll effective field theory interaction, but they didn't do density functional theory. They used their own many-body method to calculate the same properties. And we see that we get more or less similar results. It's hard to make a one-to-one comparison because their sort of Carroll EFT interaction from the two-body interaction, they go up to, I believe, next to leading order, whereas for the three-body interaction, they stay at next. The two-body interaction goes to N2LO, and the three-body interaction just goes to NLO, whereas our interactions, whenever we include the three-body force, we go up to the same order in the two-body force. So it's hard to make a one-to-one comparison, but at least the behavior is more or less the same. This is also not terribly surprising because nuclear matter properties were part of their optimization protocol. So we're just getting what we put in, but at least we're not getting anything weird coming out, which is always good. We can also calculate single particle spectra. So here I'm comparing these calculations using the UniDev family. Here I'm using with our new density matrix expansion functionals. And we see that they all give more or less similar, qualitatively, they give very similar results. I can also calculate some fission barriers. And we see that all of the different functionals, whether they're the DME functionals with or without deltas, are similar to the UniDev functionals. The only one that is different is UniDev 0, and that's because that was the first functional that didn't include fission properties in their optimization protocol. So again, we're getting sort of similar results than we had before, but we are getting an improvement when it comes to describing masses. Now, not everything is great with the density matrix expansion, and that is because, well, every time I include deltas, the performance improves, but every time I include the three-body force, actually the performance gets worse, right? So I go from next leading order with deltas, it gets better. I add the three-body force, and it gets worse. I have N2LO, I add the delta excitation, it gets better. I add the three-body force, and it actually gets worse. And if I do the same thing, but looking at not only binding energies, but also proton radii, I actually get like a similar pattern where putting deltas makes things better, putting the three-body force makes things worse. And we should expect the opposite, right? The more terms you put, the better performance you should get. So we had to look into that, like what's going on? Did we make a mistake when we derived those DME, when we did that density matrix expansion and we got these new couplings? Do we make a mistake there? Well, it seems like no. When we calculate them and we implement that in a numerical code, did I make a mistake? We review all of our work and it seems like no. So is there something going on when we do the optimization of those parameters? Well, with our collaborators at Argonne National Lab, So what they developed was this tool to make automatic diagnostics. So every time I calculate that least squares function, I'm going to check that all of the observables that I'm producing and that I'm comparing against experimental data, that they're actually physically reasonable. That is, that all the actinides are deformed the way they should be deformed. That led to 8 is actually a double magic. So there's no unphysical solution coming out of my density functional theory algorithm. And what they actually found is that there's some level of noise that has been present in all optimizations. And that actually applies also to all the unit F functionals. Also, at the same time, there was some new objective function defined. That means that some of the weights that they were given to the different type of observables were changed sort of to make it a sort of more even, more balanced in that sense. So that means that the recalibration is gonna have to be necessary, and that's what we're currently working on. So I have some preliminary results. So this is what we had before. This is what we have now with the new least squares function that we're trying to minimize. So I still see that improvement, but still, every time I add the three-body force, it's still not getting better. So it seems like even though we are fixing that noise in the optimization protocol, there's still something going on that we don't really know what's happening. This was with the least squares function. This is where I look at all the binding energies. And again, every time I add the three-body force, something gets strange. And every time I add deltas, things do get better. But every time I add the three-body force, something's not completely correct. So there's some possible explanations that we're exploring also. So just like there was some unphysical solutions during the optimization, is it possible that when I'm calculating all the masses that I have experimental data to compare with, am I also getting some unphysical solution at the same time? That's some similar checks that we have to make. Is it that maybe my density matrix expansion that I had earlier here, maybe I need to add more terms to this sort of Taylor type of series, or maybe that sort of this type of density matrix expansion is actually not appropriate for the three-body terms, right? Do I need to try a different type of density matrix expansion? Well, those are things that we are basically being explored right now. So that's when it comes to density functional theory, improving it by adding that macroscopic component. Now, can we improve these masses using machine learning? Well, first, I want to sort of recognize the work of two of my two students, Carol Galler, which is a master's student that graduated in spring of 2019, and also Matthew Crowley, that's also been working on this project. He's an undergraduate student that will graduate in spring 2021, if everything goes well, which I suspect it will. So machine learning algorithms have sort of started to be applied in many aspects of nuclear physics. And that is because, well, we've collected this data for over several decades. And in recent years, a lot of the algorithms to do machine learning, they sort of become off-the-shelf algorithms that we don't need to implement ourselves. They're already there in some packages. And we can sort of very easily sort of combine those off-the-shelf algorithms with all of this data that we have. And of course, the ultimate goal is to make reliable predictions, right? So that the R process simulations of my astrophysicist colleagues make sense. Well, I need to give them reliable predictions of what is happening on the neutron-rich side of the nuclear chart. So the machine learning algorithm typical process goes like this. First, I need to collect data. So we've been doing that for decades. Then I need to select targets. So that is what I want to predict. I also need to select something that we call the features, which are going to be my independent variables that I'm going to make use to then make predictions to get these targets. Then I'm going to take all my data and I'm going to split it into training and testing. I'm going to train my algorithm with my training data, and training the algorithm is basically minimizing a loss function, some kind of least squares function that we need to minimize. And once I've sort of trained the algorithm by minimizing this loss function, then I want to benchmark against the testing data, the data that was not used when doing the learning, sort of to make sure that I am not overfitting. It's like when you do a polynomial of very high order, and then you end up with these big changes between these points. Sort of to avoid that, we sort of benchmark against testing data and make sure that we're not overfitting. And if everything looks good, then I can go and make new predictions. But at the end of the day, something important to remember is that machine learning is just a fancy interpolator. At the end of the day, that's what it is. There's many algorithms that are available, and they all have their strengths and weaknesses. But at the end of the day, they're all fancy interpolators. So one of the algorithms that we decided to use for this approach is called the decision trees. One of the reasons we like to use them because they're actually very versatile, and it's a non-parametric approach. I don't have any parameters to adjust, and it's just going to be a series of Boolean questions in order to make a prediction or a decision. So for example, here's an example of it's lunchtime and I have to eat, but I also need to get to some doctor's appointment. So the question is, should I walk to my doctor or should I take the bus? Well, if it's raining, well, then the answer is clear. I should take the bus. But if it's sunny, well, I would like to enjoy that nice sunny weather. And then the question is, do I have enough time? How much time do I have? I have more than 30 minutes. Oh, then yeah, I should be able to walk and sort of enjoy my walk and get on time to my appointment. Versus if I have less than 30 minutes, well, I'm in a rush, so I should just take the bus. Now it's not sunny, it's actually cloudy, so I'm not actually interested in enjoying the walk. And I'm actually hungry, so I would like to eat before I get to my appointment. So what I'm going to do is I'm just going to eat while I'm walking and do that. Versus if I'm not hungry, I can just wait, and then I'm going to take the bus, go to my appointment, and after my appointment, then I'm just going to eat. Of course, nowadays, I would probably ask another question before I ask the weather. It's like, what is the positivity rate in the county? And if it's higher than a certain number, I would probably just walk. And if it's lower than a certain number, and if it's safe, I would just take the bus, taking all my precautions, of course. But as you can see, sort of the features can be numerical, like how much time do I have? What is the positivity rate in the county? But they can also be categorical. You know, what's the weather? Is it sunny or is yes or no? Is it rainy? Yes or no? Is it cloudy? Yes or no? Or, you know, how hungry I am. Am I hungry? Yes or no? So that's one of the other nice things about decision trees that allow you to combine both numerical and categorical features. Of course, the more branches I have, the more questions I can ask, and the better is going to be my description of the training data. However, one of the limitations of a decision tree is that it's very easy to overfit. So for example, here I have two examples, one where I can only ask at most 2 questions in blue. So probably the first question is my input value more or less than 3? Well, if it's less, I'm going to ask the other question, is my input value more or less than 0.5? If it's less, then this is going to be my prediction. If it's more, then this is going to be prediction. If in my first question, the answer was yes, then I'm going to ask a question, is my input value more or less than 3.75? If it's less, this is my prediction. If it's more, then this is my prediction. So that's actually one of the things about decision trees, that they don't really give like nice, smooth predictions. They're going to give sort of step functions like this. But if I ask too many questions, what happens is that a few outliers start to take over the prediction, and I sort of get something that doesn't really look at all like the overall trend I am trying to predict. So one way to fix that or to avoid that overfitting is something called the random forest. So out of my training data, I'm just going to select a subset of this training data. If I only have a few outliers, so chances are that those outliers are not going to be part of my training set. I'm going to train my tree. That is, I'm going to let the tree figure out what is the questions that it needs to ask. And then that tree is going to sort of be created on its own. Then I'm going to repeat that by, again, taking randomly data out of all the training data that I had. I'm going to create sort of slightly different questions that I'm going to be asking that are going to may result in a slightly different result. And then I'm going to do this hundreds of times. Again, as long as I don't have too many outliers. If I have too many outliers, then they're probably not outliers anymore. So most of the decision trees will not have that outlier, and therefore they will not be overtaking my prediction. And then my final prediction is just going to be the average of all of the predictions from all the different trees that I have. And that's going to be the prediction from the random forest. So that should take over. So that should sort of avoid this type of overfitting that is happening here in the green part. Well, let's try to apply this to our nuclear problem. So I'm going to follow the same algorithm as before. I'm going to collect data. Well, my data is going to be the atomic mass evaluation. That is all those experimental data that we have. And the unit F0 sort of predictions for the same type of binding energies. And then my target is going to be what we call the model discrepancy, which is just the difference between theoretical value and experimental value. I'm going to select some features. From now, I'm just going to start, well, if both my theoretical value and experimental value are a function of the number of protons and neutrons, well, it may make sense that those are going to be good features. So I'm going to use those as features. I'm going to split my data into training and testing. Typical splitting is 75 for training, 25% for testing. I'm going to train my random forest. I get a training score of, so training score usually goes between 0 and 1. 0 means bad, 1 means good. So I get something that is close to 1. These are typical values for training scores. Then I'm going to benchmark against the testing data, the data that was not used in the training. I get a 0.79. That's also a typical value. And now I'm going to improve my banding energy by saying, well, my banding energy that has this new machine learning component is going to be the theory that I had earlier for unit F0, and then I'm going to remove that model discrepancy that I had earlier. So I should get something much closer to the experimental value, as long as this machine learning that for now depends on C and N is sort of close to the real difference between theory and experiment. Well, let's see if that works. Well, here I'm plotting that difference, that model discrepancy between theory and experiment. This is the original one. This is what the random forest was able to predict. And in fact, I observed that are pretty similar. I have sort of the same, wherever I have magic numbers and the difference is greater, that's also happening here. So that looks great. If I correct my theoretical value, adding that machine learning component, actually the difference between theory and experiment gets smaller. For line nuclei, it's not so great, but also in general, DFT is not very good with line nuclei to begin with. So actually, we very rarely use DFT to make predictions in line nuclei. For that, we have ab initio calculations. So actually, it looks that is pretty well. But now the question is, what about the Neutron-rich ones, right? The ones that my astrophysical colleague needs to make his R-process simulations, right? Remember, all of my training is happening here, training and testing is happening here, but you know, what's going on here? And is going to be my machine learning algorithm reliable? Well, what happens is that my decision tree runs out of questions. And once it, like if my input of number of neutrons was 200, well, that was never one of the questions that the decision tree learned to ask, or any of the trees in the random forest learned to ask. So they're just going to say, well, I guess is whatever was the latest question I asked, which was around here. And then they all give me the same values. And I don't expect the difference between theory and experiment to stay constant in the neutron-rich area. So it actually seems like my machine learning is the least reliable where I need it the most. So what are we going to do about that? And again, this is because machine learning are terrible extrapolators. I say they were very great interpolators, but they're actually terrible extrapolators. Like if I have some classifying algorithm that, you know, I want to know if this is a picture of a dog or a cat. The internet is full of pictures of dogs and cats, and it's really good at sort of telling the difference between a dog and a cat. But if I give it a picture of a table, well, if I probably tell me I don't know, which, okay, at least I know it's not a dog or it's not a cat. But what if I give it a picture of a wolf, you know, and it might confuse it with some Siberian husky, and it tells me it's a dog when it's not. So that's actually the worst case scenario where it tells me the wrong answer. And that is because benchmarking against testing data, right? That testing data that is here, along with the training data, doesn't tell me anything of what's going on here in my predictions. And just to sort of really drive that point, we see is, you know, let's say if I want to reproduce, so e to the x, right, which is the blue line over here, I'm going to pretend that somebody make measurements, which are the orange dots. They even have some numerical noise over there. The data is between the 0 and 2 interval, but then the predictions, I want to make them in the -1 to 3 interval. And I'm going to use different machine learning algorithms. I can use a linear regression, which technically is considered machine learning. I can use a random forest. Again, you see that the random forest just goes with whatever the latest question was here and here. I can use something called the Gaussian process that also support vector machine that's even fancier. And we see that, yes, as we suspected, here when I'm extrapolating, none of them is getting anything close to the actual value. And this is also something that has been known. I mean, it's something that we should expect intuitively, but that was actually known, or it's sort of very clearly put in this paper from these proceedings in 1992, there on this conference of, even if you do deep neural network, again, the deep neural network is only going to know what's going on here. It's not going to know anything going on here and here. So how can I test that extrapolation power? Well, I'm going to imagine a situation in which I'm going to say, well, whatever the most neutron-rich nuclei that I have been measured, I'm going to pretend that they haven't been measured yet. I'm going to make the machine learning on the blue region, and then I'm going to benchmark against this testing data. And I'm going to sort of make that process sort of first just dropping the most neutron-rich one. Then I'm going to drop the two most neutron-rich ones, and so on up to 6. And what we see, the training score stays more or less constant. The testing score also stays more or less constant, but the benchmark score, yeah, the further my extrapolation is, the worse it is, right? So as we expected. So the solution is to not use the number of protons and neutrons as my feature. Fortunately, density functional theory produces a whole plethora of other properties that you can calculate, sort of a deformation parameter, what is the nuclear radii, different contributions to the total energy, pairing energies, pairing gaps. So what I'm going to do is I'm going to look for features that have similar distributions in the where I have measured nuclei and where I have non-measured nuclei. So here, for example, here's where the extrapolation is happening, where the neutron number, I have a bunch of nuclei that don't have measured values, but my training is happening here. But if instead of that, I use something like the pairing gap, well, I'm never making an extrapolation here. If I use the deformation parameter, I'm also not making any kind of extrapolations. So now I'm going to make the same process, but now the features are going to be other features like the number of protons, pairing gap, some energy corrections, deformation, spin orbit energy. I'm going to do the same process. Now my training score is more or less similar to what I had earlier. Testing score is a little lower, and that kind of also makes sense because, you know, at the end of the day, theory and experiment are a function of Z and N, and my features are no longer C and N, there's something else. But I'm going to make the same process and see, well, now my training score also stays constant. My testing score is a little lower, but it also stays more or less constant. My benchmark score is still decreasing a little bit, not as much as before, because now I'm not extrapolating as bad as I was doing earlier. And it also staying sort of around the same size as the testing score. So it does seem that now I am now avoiding those extrapolations. And now I see that I do have some structure here, which more or less makes sense to what I expect to be the difference between theory and experiment from DFT. Of course, there's limitations to this, right? There's this decrease in the testing score with these new features. Now the R process, so my benchmarking was happening sort of around here, and I'm still making extrapolations in the very neutron-rich area. So the R process is happening even further. Also, do I really expect that the model discrepancy between theory and experiment is going to be the same in both regions? So basically, it's the same question as how reliable is my density functional theory on the neutron-rich side? Well, without experimental data, the answer is we don't know, right? So we just work with what we got so far, and then eventually there'll be measurements, and then we'll be able to improve both our DFT theory and our machine learning algorithm. And do these new features that I selected, do they capture everything that I need? Well, that's sort of what we're exploring right now. So I'm just gonna go into summary and outlook because I'm also, I still have some minutes. So to summarize, so when it comes to these macroscopically constrained mean field calculations, well, we have this new family of energy density functionals that are constrained by chiral effective field theory. These are all energy density functionals with good quality and a global predictive power, or as best as they can be. We actually find this sort of surprising improvement in mass calculations. So when we look at those, we still have those sort of that structure around the magic numbers, but the difference is smaller than they were with the unitive functionals. We see that including this delta excitation from chiral effective field theory improves performance, but in adding this three-body force actually makes things worse. So we're sort of, the optimization is under review. Now, when it comes to the model discrepancy with machine learning, well, it's sort of very easy to estimate the model discrepancy. However, those direct extrapolations are not reliable, right? So selecting the features that I need to use is going to be crucial to avoid extrapolations. Even though I'm making predictions in places where I don't have any experimental values available, I am avoiding extrapolation by selecting features that are equally dense in both the regions where I have data and the regions where I don't have data. And then, so what's coming next for both of these projects? Well, when it comes to the microscopically constrained mean field calculations, we sort of need to check what other possible reasons for this underperformance when we include the triple force. So we're reviewing the calculation of all those mass tables. Do we need to put extra terms in the density matrix expansion? Something that is happening right now by some of my collaborators is, should we explore different flavors of density matrix expansion? What are the strengths and weaknesses? And once this is sort of resolved, of course, we would like to quantify the uncertainties that these models have. And they're going to have different sources. Some of them is going to be from the chiral effective field theory that had its own uncertainty. There's going to be some uncertainty due to the fact that I have to do a truncation here in the DME. And then there's going to be some uncertainty from the fact that I'm still adjusting sort of DFT or mean field parameters to reproduce some experimental data. And this is, again, of course, important to quantify. And then when it comes to the machine learning project, well, right now I'm only using the UNIDF, we're only using the UNIDF 0 functional. What happens if I use UNIDF 1 and 2? Once these DME functionals are sort of ready to be used, what happens if I use those functionals? What happens if I use any of the other SKERM functionals that exist as well? There are other type of functionals. I think one thing that would be interesting is, like, do all the corrections for all these functionals, do they all point in the same direction? Like, do I get sort of the same corrected value in the neutron-rich area, or am I getting completely new corrected values in the neutron-rich area? And then once I have these sort of corrected predictions, well, what happens when we feed them into the R-process simulations? Do the astrophysicist pattern of abundance for the different nuclei match what is being observed in the solar system? And with that, I thank you all for coming, and I would like to answer your questions. All right, thank you.
Yes, thank you very much, Rodrigo. If anyone has a question, if you could raise your hand or type it in the chat. That way, it's very good talk.
Oh, thanks.
See any questions at the moment? Let me ask a question. What about, and this is just blue skying, so you've probably thought about, I know it's mixing, you know, methods. What about using some methods like couple cluster to at least provide data on near spherical nuclei, which is more microscopic? Thought we got a bunch of questions.
So you mean sort of in the machine learning part? Like,
yeah.
I think, well, I would need to think about that, right? Because, like, so you're saying the theory is going to have some DFT part and some coupled cluster part here as well?
Yeah, I'm just sort of throwing out, I haven't thought.
Yeah, no, I understand. I think there's things that can be explored, but then at the end of the day, I still want to make predictions sort of in this region over here. And right now, DFT is the only one that can make predictions here. I can try to improve them with machine learning. Now, is my improvement with machine learning reliable or not? Now, going into these sort of features that are not extrapolating, can maybe coupled cluster say anything about if it cannot calculate sort of the binding energy, can we calculate maybe some deformation properties? I don't know if coupled cluster can do that in sort of the neutron-rich area. Even if you cannot calculate the binding energy on its own, can you at least say something about the deformation just based on the number of neutrons and protons? So that could be useful, because then even if you don't have sort of the binding energy that you want to correct, you may still have some information that you can use as a feature. And you can use.
Although coupled cluster tends to be really terrible with deformation. So
okay. But yeah, again, so there's different features that you can try, and then the question is, like, can I use those? Can my features come from coupled cluster? Well, I mean, if I can calculate them everywhere, then yes, right? It doesn't have to be deformation. It can be something else. As long as I can calculate it everywhere, then yeah, I can sort of inform it.
I see.
Yeah.
So we do have some questions in the chat. Oliver asked, could you explain more about the non-locality of the chiral EFT terms you added?
Yeah. So let me go back here. Well, the non-locality is always there here, right? So this is how I calculate. So there's two terms in DFT or in Hartree-Fock Bogey-Lebov. There's the energy from the Hartree term, which is the direct term, and then the Fock term, which comes from having some anti-symmetrization operator here. So this sort of non-local density is always here. Now, when I use a purely skirm or purely UniDef functional, what happens is that that functional has some delta functions here, and that allows me to basically do the first integral over r, over little r. So the delta function is on little r. So then the first integral is just evaluating the other integral with little r equal to 0. So then this goes away, this goes away, this goes away, and then I end up with local densities, right? That is what happens when I have skirm, any kind of skirm interaction. Now, when instead of using the skirm interaction, I put the realistic one, then I can no longer sort of get rid of this little r. And then I do have to deal with this non-local density. And one way to do it is by doing what's called the density matrix expansion, which is I'm going to expand it around the local one and its derivatives. And then there's this extra function. So the different flavors of DME is actually which function do you use here. So you see that big R is only in the density and little r is in the other terms. So in these functions here. And basically the type of function that usually these are some spherical spherical Bessel functions is what you have here and here, that they have some nice, like, you know, they go to, when little r goes to 0, they don't blow up. And when r is big, they do go to 0, stuff like that, those properties that you need to have here. And that's sort of what takes care of this. Now I can take these, plug those in here. I still need to make these ugly integrals, and those are done numerically. But one of the advantages is that this is independent of which nuclei I'm calculating, whether it's calcium or lead or oganesum. Like, it's going to be the same. So actually calculating these intervals, I just need to calculate them once, and then I can just use those values everywhere else.
Rodrigo,
yep.
The density matrix expansion, is that very complicated because you only have a first order expansion here?
Yes. So, well, actually, this is a second order derivative, if I remember correctly. But yeah, right. And then the question is, like, do we need more of these terms? Because the derivative force seems to not be working for some reason, right? Or do I need to use a different flavor, something here, a different function here and here? But yeah. What other questions?
So the next question is from John. What software is being used for the random forest?
So I'm relying, like, as I said, now that all of these algorithms have sort of become off the shelf. So it's scikit-learn from Python. The good thing is that there's like a lot of documentation online. One of the bad things about it is that, especially when you're starting, it can be very easy to just sort of treat it as a black box and not, you know, there's a lot of arguments for all of these functions. Like, do you want to use the default values, or does your problem require to change some of those values? So there's a little of digging that has to go into it to sort of to make sure that you're using the right tool for your problem. But yeah, it's scikit-learn, and there's like a lot of documentation online for that, and also a lot of resources for that. Right.
The next question is, you mentioned DFT isn't good for light nuclei. Do you mean compared to the ab initio calculations?
Well, yes. So as I was saying, like, right, like if we look at sort of the light nuclei, you see that the difference between theory and experiment is actually the largest here. And that is because when you're doing the mean field, when you do this approximation, if you only have 6 nuclei, well, then it actually makes more sense to do the ab initio one, because then you're sort of this this average interaction sort of is assuming that you have a lot of them, sort of that you can actually have, so that the average actually sort of, it's a good proxy for all of these interactions. If you only have a few of them, then it's not going to work so well. And that's sort of what's happening here. You know, the same is happening here. See that the difference are greatest here. In fact, I think here the lightest ones are not even included, but if this other figure, where I put them all, they're actually included here. So you see the difference is greatest here. But yeah.
So the next question is again also from Harrison. In practice, do you weight features when using a random forest?
No, in practice, they are all equal. So you do have to scale them, which basically sort of like if I look here, where was that? here. Like, for example, this feature goes from 0 to 300, whereas this feature goes from -1 to 3, and this feature goes from -0.2 to 4. So you do need to scale them so that they're all within a certain range. Basically, you try to normalize, even if the distribution is not a Gaussian, you do want them to sort of have a mean of 0 and a standard deviation of 1. But once you scale them all together, then you sort of use them all the same. Because if you don't scale them, then sort of these big numbers are going to sort of dominate the whatever is happening in the random forest.
And then John asked another question. What compute power for the DFT and the random forest is needed?
Oh, something like I do it on a laptop. There's nothing. Oh, sorry, for the random forest. Yeah, the DFT. So a single DFT calculations you can also run on a laptop. Now, when you need to calculate all of this, we're talking about tens of thousands of nuclei. So each one of these, a single DFT can take like a few minutes on a regular desktop computer or a laptop. But once you have calculated tens of thousands, then you have like hundreds of thousands of minutes. And that, if you want to calculate like a whole nuclear chart, you do need like a big computer, a big cluster. The random forest, it's a regular computer.
And I basically answered this question, but the question was how far off from masses the experimental masses, and do the organizations agree and update every couple of years?
Well, one of the things is that the experimental values have like error bars in the order of kilo electron volts, whereas the difference between theory and experiment you see here, where this here. So this is in mega electron volts, if I remember correctly. So you have like the experimental uncertainty, the statistical uncertainty of the measurement is actually several orders of magnitude smaller than the theoretical uncertainty. So even if there's updates on the experimental values, the difference is still dominated by the fact that the theory is not at the same level yet. And you're probably going to need a lot more computing power to get it to the same level. Like, it's not going to be something that a single DFT calculation you can run on a laptop or a desktop. Because, yeah, there's this big mismatch between the experimental uncertainty and the theoretical error. But yeah.
Okay. Are there any other questions people have? Well, we're ending right on time. We're just about perfectly on time.
All right.
Very good discipline. There you go.
All right.
I want to.
So thank you. Very good talk.
Thanks. Oh, thank you all for the invitation. Well,
thank you, Rodrigo. Very nice talk. And thank you, everybody, for attending. And have a nice weekend.
Yeah. Have a nice weekend.